7, 8, and 9. And we have another sequence, so there is a position 0 that has nothing. There is another sequence that starts with, that is A, B, I'm sorry, can I see this? Okay. A, B, B, C, D, D, B, and A. And this would be 1, 2, 3, 4, 5, 6, 7, and 8. So you do remember from the dynamic programming algorithm that this is a matrix that you have to fill. And you fill it by having the first row being zeros and the first column being zeros. And thereafter you have to match elements together to find what to put into the matrix. All right. So I'm going to put the elements that matter in red and the elements that don't matter in blue. So what does it mean for an element to matter and not matter? So we are going to see what we can put here into this entry of the matrix. So you see this element here will be either the maximum of 1 plus, if there is a match, you take the maximum of 1 plus what you have here and these entries. So you will see that there is a change, so there is a 1 here, which, in the original algorithm, what I described to you, you would have put this kind of arrow over 1, which means it goes up diagonally to the 0. And then thereafter, you continue here. You see there is a, so I'm going to just put the numbers. There is no match. So because there is no match, you take the maximum is going to be this guy. There is no match. There is no match. There is a match over here, but the maximum is over here. So I'm going to not consider this path, but just this. And this continues this way until the very end. So I'm going to put, so there are two things I did. If I had to move diagonally up, I put it in there. If there were two possibilities, for example here, to either move diagonally up or in this direction, I took the direction that was not the diagonal direction. So whenever I got these diagonal elements, I will put them in red. So then we go with the B part. The B, you put a 1 here, which is the maximum of these two guys. But at this point, you see, you will have a what? A 2, exactly. And this 2 is an element that matters. So I'm going to put a 2 over here. And thereafter, everything will be 2. You agree so far? Okay. So next element is again B. So we put a 1 here because this is the maximum of these two entries. Here we have two possibilities. Either we take the maximum of these two entries or we take 1 plus this entry. I choose to take, because there is another way, sorry, there's a 2 here, because there is another way of getting a 2 other than adding 1 to the diagonal entry, I choose to take that way. So B and C don't match, so there is a 2, B and C don't match, don't match, don't match, don't match, don't match. But at this point there is a match, and I put a 3. Okay? I continue here, I get a 1 here, I get a 2 here, and what do I get here? I get a 3. So I'm going to put this 3 again as something that matters. And then what do I get here? Also a 3 in two different ways. Either I go up this way or I go this way. So because there is another way of getting a 3 other than going diagonally up, it's an element that does not matter for me. And same way here. So I have 3's over here. Then I go with D. So there is a 1 here, there's a 2 here, there's a 3, 3, 3, and what do I get here? A 4, right? And that would be something that matters. So I put a 4 over here, and there will be 4s thereafter. So here again, I have a 1, I have a 2, I have a 3, 3, 3, and I have another 4, but this 4 is either 1 plus 3 or this maximum, so I just put it in blue, and thereafter I have 4s everywhere. So here again I have a 1, and I have a 2 here that I can get in 2 different ways. Either I take the maximum of these 2 entries, which is a 2 or 1 plus here, so since there are 2 different ways, I'm going to put a 2 in blue, a 3, 3, a 3, a 4, a 4, a 4, and what comes here? It's a 5, right? Because, you know, B and B match, and again, an element that matters. And eventually I arrive at A. So A, again, I can get this 1 in 2 possible ways, either as the maximum of these 2 entries or 1 plus this. So this becomes an element that does not matter. So I have 2, I have 3, I have 3. Well, I have a 4 here, right? So this does matter. So I'm just going to put a 4 over here. And thereafter I have 4s and 4s, and here I have a 5, and thereafter I have a 5. Okay. Now you will you will see a structure in this matrix that we constructed this way. And the structure is that you can, if you look at the 1s, for example, the 1s will have a dominating so all these guys are 1s, right? If you look at the 2s, well, you know, this means everything here is a 1, and possibly underneath you also have 1s. In this case, there is nothing underneath, but here you will have that. So if you look at the 2s, then you will find that you have this structure. If you look at the 3s, you will find that you have this structure. If you look at the 4s, you will find that you have this structure. And if you look at the 5s, you will find that you have this structure. So you see this, you know, all that matters here. So by the way, when you look at these numbers here, do you see how to get the largest common subsequence just from the position of these elements that matter? So this corresponds to the, when you look at the dynamic programming approach, you would have to go sort of diagonally up from these elements. So, but you know, if you look at these elements, is there something that you can say about them? If you look at these lines that I drew, is there something that you can say about them? They're exactly the antichains. That's what they are. They're exactly the antichains in the LCS algorithm. So the antichain approach that we developed last time doesn't come from, you know, from outer space. It comes from looking at this algorithm and seeing where could I save something, right? So if you, so by the way, these algorithms are all due to a person by the name of Hirschberg, who, well, Hirschberg actually, because he was American, not German. And so he developed it when he was at Stanford University in 1975. So the dynamic programming approach and the next one. And in fact, what I had to do, because of your questions last time, I actually went back to the original paper and started reading it. And it's a very interesting read. It's not so easy to read, but you know, once you understand what he's doing, it's actually very nice. Because he does explain in the paper. He says, okay, we have this quadratic time algorithm, or this algorithm that has a running time of m times n. Is there any way we could possibly improve this dynamic programming approach? And then he goes on in the paper and says, well, let's look. I mean, what did we do? Essentially, we created this matrix the way it is here. He doesn't, in his paper, he doesn't talk about anti-chains or chains or Dilworth's theorem, nothing like that. He actually develops things sort of by foot, more or less. So he says, all right, where am I spending too much time? At the end of the day, I'm really interested in these elements that matter, because when I connect them this way, I get, in our language, the anti-chains, and when I have the anti-chains, I just need to sort of go up and then find my element from these anti-chains, the way we learned it last time. And then he says, well, so if this is all I need to find, why am I doing all this work and trying to find all the other entries of the matrix? Well, the answer, he essentially answers that and says, well, I'm doing this because this is what dynamic programming does. Dynamic programming just calculates a hell of a lot of other things in order to eventually get to what we want. But maybe there is a better way to do this. And then he develops the algorithm that I showed you last time. And he says, this is the better way to do this. Because what I need to do is I sort of need to scan. Okay, so first of all, what I need to do is I need to find matches. The point is, you know, a lot of this matrix is useless. You know, if there is no match somewhere between the points, so when you look at this A, the only points of this row that matter is when A has a match, when there is a match. So there is an A here, and there is an A in the other sequence. So the only points that would matter in this row would be this guy, and this guy. Right? The only points that would matter in this row would be, well, this guy and this guy, and so on and so on. So in order to find the elements that matter, I don't have to look at places where there is no match. That would be stupid to do it, because certainly these elements that matter would not appear at places where there are no matches. So this is the insight. This is the big insight that leads to a faster algorithm. And this is why we started looking at this matrix where you only have, you know, where you only look at the matches between the elements. Is that kind of better understood at this point? So you can see that this faster algorithm doesn't really come from nowhere, right? It comes from an attempt to modify and better the algorithm, the previous algorithm. And you know, there is no there is no secret here. The same person developed both. So, you know, and unless he was schizophrenic, obviously there is a connection between it. Okay, so now I need to pay my debt. And my debt was to tell you why this algorithm is that the algorithm? Yes, I guess it is. Yes. No, right? Yes. So why this algorithm actually runs in time n times p, where n is the length of the shorter sequence and p is the size of the longest common subsequence. The answer is, it does not really. That's part of the answer. But you have to be very subtle to understand why not. And you have to understand the model in which we are going to do this. So somebody asked me last time, who was this? Can't really. Somebody asked me and said, hold on. If you want to find the match matrix, so in other words, let me give you another way of looking at this. So I'm going to put down the elements again: A, B, C, C, A, D, C, A, B. And here I'm going to put down A, B, B, C, D, D, B, and A. And so the match matrix is, you're going to put a dot whenever there is a match. So again, we are going to put a dot here and here. We are going to put a dot here, here, and here. We're going to put a dot here, and here, and again here, and here, and here, here, and here. So this is sort of the match matrix, right? So the question, who was that who asked me this question in the break? No? Maybe the person is not here. Okay, doesn't matter. So the question was, even if you want to write down this match matrix, you need m times n at least space, in the worst case. Because, it could be that everything matches and you have to sort of, and if you have so much space, at least you may need so much time as well, because you have to examine every entry to see whether you have to put a dot in or not. Absolutely correct. So this means that we are not going to do it this way. We're going to do it a little more intelligently. And the way we are going, so if you look at, this algorithm, you will find that we are going to go row by row through this matrix, and at every row we are going to find the minimum position, the minimum column where there is a match. And so I think you asked me last time was, even if you want to find this minimum, you need you need the length, the number of columns time. So there again, you need your algorithm will run in time m times n, where m and n are the length of the sequences. Absolutely correct. But this is not the way we are going to do it in an actual algorithm. In an actual algorithm that makes this work, and this is where the subtlety comes in, what we are going to do, we are going to distinguish two cases. In the first case, we are going to assume that we know sigma, which is the alphabet of the strings. So in other words, sigma is the smallest number of distinct elements, characters, that appear in these two strings. That is the alphabet over which we are working. And then what we are going to do is we are going to sweep linearly through the sequences and create inverse lists. So we have the sequence X, which is a sequence with m characters, and we have a sequence Y, which is a sequence with n characters. And what we're going to do is we're going to create inverse lists. So let's say I'm assuming that n is less than or equal to m. Doesn't matter, but one of them is certainly less than or equal to the other. So I'm assuming y is less than or equal to x. So we're going to so for every sigma in sigma, what we are going to do is we are going to create a list, an ordered list, L of sigma, and this is the ordered list of all I, or all, well, of all j, such that yj equals sigma. So in other words, what we are going to do, so how would we generate this ordered list? Ordered list, it's actually pretty simple to generate. So suppose that y is what I had before, A, B, B, C, D, D, B, and A. Okay? So then I would have, so I know the alphabet beforehand. In fact, I can actually generate the alphabet by sweeping over the sequence X, sweeping over the sequence Y, and collecting the distinct entries. There is an algorithm that is associated with it that I'm not going to discuss, but let's for now assume that we actually know the alphabet beforehand. This is the case that is most often given. For example, if you want to do a diff between two files, you know the alphabet is bytes. So you know all the bytes beforehand. So what I'm going to do is I'm going to sweep through Y and update the list. So the list, I know I will have to create a list for A, a list for B, a list for C, and a list for D. So I'm going to sweep through Y, and the minute I see an element, I will add it to the list for that element. So I see an A, and I see, aha, so A appeared at position 1, so I'm going to put a 1 here. The next element is a 2, okay, so I'm going to put a 2 here. The next element is a 3, so I'm going to put a 3 here. The next element is a C, and it's at position 4. The next one is a D at position 5. The next one is a D at position 6. The next one is a B at position 7. The next one is an A at position 8, and I'm done, so I'm going to close all my tabs. What happened?
L of A is 180.
Ah, thank you. Okay. All right. So this is what, this is the pre-computation that my algorithm needs. Because with this pre-computation, what I can do is when I hit, so when you look at this, when I hit one of these rows, then what I will do is I look at A and I see, aha, I need to find the positions of A in my sequence, and I need to find the smallest one. So I just scan through the L of A sequence and just take the first entry. Okay? And so on, and so on, and so on. So this is the reverse list that we need to build. Now, how much time do we need to build? So you agree that that's all that this algorithm needs, because this is what you need. This is what you need to find, and this you can do with this reverse list. How much time do I need to build up such a thing? So now this depends on the sigma, on the size of the sigma. When sigma is constant, then, well, you just allocate these things, and the time is essentially the time you need to sweep through the sequence, which is n. It's linear time. But when sigma is big, or even moderate size, then for every one of these entries that you have, you need to go through a sequence of these A's, and because you don't, when sigma is big, you have a large list, and you don't have a random access to positions of this list. So you have to do a binary search to find where in this list this element is, and then start putting the corresponding index into the set. So for every, so in that case, the running time of this step would be, well, the size of the list that you have, and then in order to determine where to put the element, you need that many comparisons. Because this is the time you need to figure out where in this list you have to put. Just imagine this list being very long. You need to, and you don't have random access to the point, so you have to do some kind of a binary search to get to the point. Yes?
Can you use a hash map?
You can use a hash map, but if the list is long, again, you need a pretty large hash map in order to avoid collisions. So, this is actually, you see, this thing, in fact, comes up when you don't know the alphabet beforehand. If you don't know the alphabet beforehand, then hash maps don't even work. Because, you don't know. Well, they actually work. It's not that they don't work. They work. But, the point is that if this is long, even in the hash map, you need to find which hash entry to go to. Either your hash table is small, in which case you have lots of collisions, or your hash table is large, in which case you don't have lots of collisions, but still you have to figure out where to go. So the truth is that this is the kind of thing you need to do for the pre-computation. The other truth is that when in practice your sigma is small, so the log of sigma is a constant, and you have linear time precomputation, and then O of n times p for the actual algorithm. Is that an adequate answer to your questions from last time? Are you satisfied? Good. Well, thank you for asking this question, because otherwise I would not have looked at the paper, which is very good, because usually you look up these things in books and other places. Sometimes it's much nicer to go to the actual papers. All right. So what did we learn? We learned that the faster LCS algorithm is just an attempt to make the original LCS algorithm faster, and it is not something that you get by looking at partially ordered sets. Partially ordered sets give you a very nice way of concisely describing the algorithm. But actually you want to find the elements that matter. Okay, are we good? Should we go to the next chapter? Good. Yes, please.
Is the sigma only the letters in Y or both X and
Oh, so sigma is the entire alphabet. It's the distinct letters that appear in X and Y.
sigma is not, but what if we are using very little letters in Y? So
If you use very little, if you use yes, if you use very few letters in Y, then the size of well, actually, the way I described it, it is what is in Y. So if you use very little, few letters in Y, then sort of the matches that you find in the matrix will be confined to a very small number of rows, right?
isn't it better to go through Y once and discover which letters that we are using so that we don't deal with whole sigma?
I see. So one of the questions is, if let's say your sequence Y, it turns out, has very few letters compared to the sequence X, isn't it better to just do things ad hoc? Is that's the answer is it may be, and you can, however, reduce the case that I was just describing. You reduce your case to mine in the following way: you go through the letters of Y, and then you identify them. You go through the letters of X. If there is a letter of X that does not appear in Y, you might as well throw it out. And then you make your X much smaller, and then you are back to the case where X and Y share the same. For every letter in Y, there is at least one letter in X. Because certainly if that letter doesn't appear in X, there is no match, so we can forget it. So by the way, this algorithm is an algorithm that's, so you guys know the command diff in Unix? Who has used diff? D-I-F-F. Very few people. Interesting. You always work with the graphical interface, because then you can't use diff. If you use command lines, you're bound to use diff every once in a while, right? I definitely recommend using command line, but that's me. I see I have a follower here in the audience. Yes. Anyway, so diff is a utility in Unix-based systems that find differences between files, as the name suggests, DIFF. So, for example, it's very important if you have two files that are slight modifications of one another, or one is a slight modification of the other, and you want to find, which part is the modified part. It's extremely important when you develop code. Is that how you use diff? Because you develop code? When you develop code, then what happens is that, usually when you develop code, there are bugs in there. That's just a rule of life. There are bugs, and these bugs, usually you find these bugs maybe after a year or so. That's the worst part, because at that point you of course don't. Anyway, so sometimes, and that's also a fact of life, these bugs are just because maybe you didn't initialize a variable, or maybe you wrote minus instead of a plus. I don't know, this kind of stuff. So what you want to do is you want to patch your original data with a little bit of file that says, go there and change this. And this utility, which is called patch, by the way, also uses diff and also uses this kind of algorithms to determine where we're. So it's a very important algorithm to find longest common subsequences. Okay. So the next type of algorithms that we are going to discuss is called greedy algorithms. So greedy algorithms, as the name suggests, do something that is greedy. So being greedy means that, actually I'm not sure it actually means that, but anyways, what a greedy algorithm does is it tries to maximize a utility function according to very local information. So this is what a lot of people perhaps associate with greed. So with greed, if you are greedy as a person and you want to maybe accumulate money, but you don't necessarily look over a long period and what other people, what kind of an effect your behavior has on many other people, and you just try to maximize a utility function which is immediately increase the amount of money that I have. So whenever you get such a chance, you try to increase it. That's typically what people call greedy behavior. So greedy behavior is also, you see that in a traffic jam. Maybe not in Switzerland, but you see that in many other countries, including the east coast of the US where I used to live for a while. So you have a traffic jam, and if everybody is smart, they know they just stay in this traffic jam until it's resolved and then everybody can go home. But no, people are greedy, so they use the access lane, right? I've seen that, believe me. So they use the access lane. Sometimes they use 2 cars using the access lane that is actually meant for 1 car. So sometimes, I've seen trucks making U-turns on highways. I mean, all these things. So this is greedy behavior, okay? Because you try to maximize a utility function, and driving is one of those cases. If you don't collaborate and you're greedy, then everything breaks down. Okay, so greedy behavior typically is not good. In algorithm design, it's a slightly different world. Sometimes you don't know any better to design an algorithm than to locally maximize some utility function. So for example, you want to schedule jobs on processors. Okay, so, and these jobs, they will take certain amounts of time. So you tell to yourself, look, I'm going to, maybe, my greedy behavior is to say that I want to process as many jobs as possible. So that's my local utility function. So what am I going to do? I'm just going to grab the jobs that have the shortest time and put them on available processors. Is that a good thing or a bad thing? Depends. Some other person comes and says, well, what I really would like to do is I would like to maybe minimize I/O, whatever. I'm going to take the jobs that have the longest running time and put them on processors. And then let's see what happens to the smaller jobs. I don't know. Maybe I can fill them in every once in a while. That's another type of greedy algorithm. I've prepared for you one type of greedy algorithm that people actually use, and is not that bad, and that is to schedule classrooms to classes and professors. I don't know whether SAC uses that here. I don't know. Certainly I'm not going to go to them and say, you're using a greedy algorithm. They will not like that. But in any event, this is how we have, and this could also be applied to scheduling jobs on processors. So we have n professors, and these n professors want to use the same classroom, like for example this one, CM1. And every professor has a preference for the time interval he or she wants to use the classroom. So in our case, maybe the preference is what, again, Zach gave us and said, you know, you teach on Fridays from, whatever, 13:15 to 15. So to each professor belongs a half-open interval. So the ith professor has a start time SI and an end time or finishing time FI. So this goes with every professor. Now, what the organizer of this room wants to do, he wants to find the largest subset of the professors that the organizer can schedule, that the organizer can put in the room without having any conflicts. And a conflict is when two professors have to use the room the same time. Okay, so in other words, you want to find the largest subset of the set 1 through n, such that the interval corresponding, so for every I in that subset, the interval, or I and j, the interval corresponding to the ith professor intersected with the interval corresponding to the jth professor is the empty set. Is the task clear? That's what we want to do. Okay. So, let's see how we would possibly try to do this. We could look at the finishing times of these professors and say, well, when do they actually finish their courses? Because, you see, you can only start another course when when the previous professor has actually finished his or her course. So we take the finishing times of these professors and we order them in increasing order. Okay, F1, F2, up to Fn. And that we can do in time n log n. For example, using merge sort. And we will learn other sorting methods later in this class. So, and then what happens? So we have sorted this sequence, and we are going to find a subset of 1 through n that such that in this subset no two professors have a conflict. So how are we going to do this? Well, we are going to pick the first start. So we are going to take the finishing time. So we have now the finishing times. These are the finishing times, and they're ordered in increasing order. So to the finishing time F1, there corresponds an interval. So this would be S1. That would be the first professor. We do schedule the first professor that way. So which means that professors who are willing to wake up early, they have a better chance to get the room, right? Because their finishing time will probably be earlier than any other person's finishing time. So maybe there are other professors here. Maybe there is another one that has so maybe there is another one that has this finishing time, and maybe there is another one that has also this finishing time, and so on and so on. So among these, so we look at the professors whose finishing time is F2. And we pick the one that has a starting time bigger than F1. So, you know, obviously once we have scheduled this guy over here, we cannot schedule this professor anymore because there would be an overlap. So the first one that we could schedule is this guy over there. So that would be the second one. And so on and so on. So then we go to the other finishing. It could be that we cannot actually have one of these finishing times because it's possible, you know, that there is some kind of other overlap, because, you know, it could be that there is another. So this is F4. It could be that I have there is a professor who starts here and goes all the way to F4. And maybe there is another professor who starts I don't know, here, and goes all the way to F3 or something. So I would probably schedule this one. So, I'm going to go through this list, and I'm going to look at the starting times, and look at when there is a starting time that's bigger than this finishing time, Fj, and I'm going to schedule this guy Si, and let the next finishing time be the finishing time of that job, of that guy Si, and continue doing this. Is that clear how we're going to do this? Should I have an example, maybe? Okay, let's have an example. I need to just create one on the fly. Okay, so let's see. Let's say, just going to put 1, 2, 3, 4, 5. These are the hours. And maybe there is a job here. There is a job, I don't know, here. There is a job here. There is one, I don't know, there is one maybe here. There is one here. There is one here. And maybe there is one here. And then there is one here. So these are the professors and their starting times and finishing times. Okay? All right, so what is the ordered sequence of finishing times? So this would be professor number 1, 2, 3, 4, 5, 6, 7, and 8. So there are 8 professors fighting for this valuable resource. Okay, so what is F1? Well, actually, we need to sort according to the finishing times. So what's the first finishing time that we see? No, this is the starting time. The first finishing time that we see is, I think, 3, right? Okay. So this would correspond to F1. What's the next finishing time we see? It's 4, so it would correspond to F2. What's the next one that we see? This one, right? So F3. This is just a little bit not good, so sorry. Let me grab this so you can see what's going on here. So what's the next finishing time that we see? Is this guy, right? Is 6. So it would be F6. The next finishing time, I'm just going to finish this, then we can... what's the next finishing time? 7, so it would be F4. The next one is 8, so it would be F7. And then we have, F5 and F8. So this would be the ordered list of finishing times. If you just allow me a few minutes to run the algorithm, then we'll see. Okay? So what are we going to do? We are going to put the first guy is lucky. He will always be there. So this list will contain 1. So we have identified 1, and at this point, this finishing time, so we have scheduled the class over this entire interval. So certainly we cannot schedule anyone who has a conflict with this interval. So we cannot schedule this guy, and we cannot schedule this guy. What we can schedule, so we go through the list and see, F2 cannot be scheduled, F3 cannot be scheduled. The next job that comes along is the 6th one. That's this guy. Oh, this guy can be scheduled, right? Because it doesn't have a conflict with the first guy. So this would be, the next element would be 6. And then we are going to again look at anyone who has a conflict at this point, right? So what's happening here? Okay. So we have to go over here and look at everyone who's... no, there is something wrong here. Maybe we take a break and I take a look at this example. Thank you. I need one too.